Okay, fine. Okay, so right. So we're here for the second session. So today, we're very happy to have David Colliaux from Sony. So I've been read his work a long time ago. And very impressive. And so I'm very happy to have him today. So he will be presenting some decision making and information transfer, or at least some basis of decision making and information transfer for biological systems that do not have neural networks, like we don't have central nervous systems. And so I find this subject fascinating, especially how you can replace neurons at a biochemical level. So go ahead.
Thank you, Grégoire, and thank you for having me. So I present the work we did with Jacques Droulez, Pierre Bessières, Claude Duprémian, and Guy Giraud. So Jacques Droulez and Pierre Bessières are theoreticians, and Claude Duprémian is the person in charge of the algae collection in the Muséum d'Histoire Naturelle, and Guy Giraud is an artist with whom I did the experiments. So, as Grégoire said, you can look at this microalgae. So it's Clavidomonas renarti, and it appears to have agency, like it moves toward the light, or it can move away from light. And so it's intriguing to know how it can achieve such behavior. Actually, it's not too complicated to implement the same behavior in robots. You can see if you have two receptors at the front of a robot and they inhibit the action of the wheel, they will naturally go towards the light, and you just have to cross the connection and they will escape from the light. So you can have very simple models to reproduce the behavior. And actually, you see here the algae, if you put light on this side, in some conditions, they will escape the light. In the petri dish, they add some special liquid, and then the algae goes towards the light, and then they add a buffer to this agent, and the algae escape again. So it appears that there is very simple basic mechanisms to do the equivalent of crossing the connections here. And so, yeah, I'm interested in this organism because, as Grégoire evoked, often when we speak about agency and cognition, we think of brain and neurons. And for example, one popular theory of brain science is Bayesian brain hypothesis. And if we look at algae, there appears to have to do the equivalent of Bayesian computation, but without neurons. So how can they do this? It's kind of a hard question. And so just to tell you, there are many paths towards phototaxis. There are many kinds of phototaxis. And here I'm focusing just on two of these, the Clavidomonas renarti you see here. So here is the eye spot where it sees light. It's like a 1 pixel camera, if you will. And here we have the flagella. It's a organelle that it moves to swim towards or away from the light. And here another organism I've been doing experiments with also is Euglena gracilis, which has only one flagella, but a longer one. And you can also perform phototaxis. But so first, I want to start with general consideration about how we can implement Bayesian computation through biochemical networks. And this actually is a work that was already started by Jacques and Pierre when I joined their team. And so I participated in this and tried to show how it can be interesting for modeling phototaxis. So first, we need to say what we mean by probability computation. So the basic object is that of what we call the Bayesian subjective model, and it includes observations like data, state of the world that you want to infer, and possibly some latent variables. And then you can apply the Bayes formula to invert the probabilities. So suppose that you know the probability of data knowing the states of the world. You can infer the probabilities of the state of the world knowing the data by summing over latent variables and normalizing by this term. Then what do we mean by biochemical cascade? So here I will take a very restricted definition of what a biochemical cascade is. So I suppose that we have two types of entities, the messengers and the macromolecules. And the messengers are produced and removed through the action of the macromolecules. Okay? And so messengers, they have only one state. Macromolecules, they have multiple states. Messengers, they are mobile, and macromolecules, they are supposed to be static at the scale we observe them. And examples of messengers are G-protein alpha subunits, cyclic nucleotides, plastic calcium, or you can even include membrane potential. And for macromolecules, examples are receptors, ionic channels, or activable enzymes.
So will you explain the cubes?
Yes, I will explain later. I want just to state what I will try to show you, that for any Bayesian subjective models on discrete variables, you can find a biochemical cascade that will which stationary states amounts to the computation, the same computation as the Bayesian subjective models, and the reverse is true. And yes, just to give you a hint of how it works, is that both involves only rational function with non-negative coefficients. So we'll go through it. So first, from Bayesian subjective model to rational function with non-negative coefficients. So this is quite simple. So you take the formula I showed before, the Bayes formula developed for the latent variables. So usually this is intractable to compute because the space is so huge. So what you can do is you take a state of reference. For us, the state of reference is S equals 0, which is kind of the default state of the world. And you divide everything by P of S equals 0. And you can write the posterior as a rational function of the priors and likelihood ratio where you divide by probability of the default state. So this is the easy part.
So maybe can you explain what is S, L? So L is latent. So in BSM, so what is BSM already?
Bayesian subjective model.
And so but includes data observation, state of the world, then latent variables. Okay. So it's just it's just the one hidden variable, for example, one observation and one model of the state of the world condition to the latent variable.
So and for this, so you see, you will have only multiplications and sum and ratio, and everything is positive, so the computation is just a rational function with a non-negative coefficient. So then a bit more tricky is how the reverse path from rational function with non-negative coefficient to Bayesian subjective model. So for this, we need to know how we will combine two models, and this is earlier work by Pierre and his team that you can find in this book. So when you have a Bayesian subjective model with S1, D1 and L1, sorry, here I used F, but it should be L. So, and the second BSM with S2, L2, D2, you can combine them by building the probability distribution over the variable S, D, and all the variables of the submodels. You add some additional what they call the coherence variables, gamma. So the probability for the coherence variables given the data is given by the indicatrix function of the data. So it is one only when the data in the two models match. And then you can parameterize what is the probability of lambda being one given the states of two submodels and the global model. So these are your parameters, and you end up with yes, so you can do the computation. And so here I take only with binary variables, you end up the mixed model, the model combining the two submodels have this kind of odds for the states. And then you can choose the parameters here to be so that the odds is either the product, the sum, or the ratio. So you can choose to parameterize the combined model here as you wish to create the sum, the product, or the ratio. And so then when you have a rational function with a non-negative coefficient, you can decompose gradually into simpler and simpler functions, where each step you use one of the operation plus, multiply, or divide, and you will end up with a Bayesian model, which inference amounts to the computation of the rational function you decided before. Is it clear, or do you want me to write something?
Now, for me, it's not completely clear. So for any rational function, you can associate. So any rational function, you can associate BSM.
Yes.
So that's the operation you did just before.
Sorry?
That's the operation you did just before.
Well, the operation we did here is how we combine two BSM into a global BSM, a more general BSM, which combines the two sub BSM.
Okay.
And we show that we can,
so because you want to do
we can build different global models by changing the parameters here. Okay, and actually by choosing the parameters properly, we can choose the global model to be the product, the sum of the ratio of the odds of the submodels. Yes.
Yeah. Okay.
And so, if you have any RFNC, rational function with non-negative coefficient, you can say first, I say this is, let's take the ratio, for example, if it's A of x1, x2,
Can erase the.
Yes. So if you can write the if the function you are after looks like this, you say, okay, I will build a BSM for A, a BSM for B, and I have a recipe to build a BSM for the ratio of A and B, of A over B. Okay?
Yeah.
Because you can choose just to put this one to one, this one to one, and the others to 0.
Where I'm confused is X here, the variable corresponds in the DSM to the values of the distribution, right? X here is something. So H1X, what is X? X is a state. X is
X is a state, yeah.
Yeah. Okay.
Yes.
So H1X is
but
probability
actually
of the
it's
states.
abstract.
So
it's
about-
abstract
no,
because we are trying to build a BSM for a function.
Yeah.
Yes. So we are after this function. So
What I mean is that
H of X is the function of the submodel 1 for which you have a BSM.
yes, but it needs to be so on one side you have a function on the variables in R or Rn. It's a rational function, and on the other side you have a distribution over states. So I imagine that the variable is the set of distributions over states, right?
Okay.
No. If you take a x, for example, h1x equals x, what is this is a rational function, right?
Yes.
So what is the BSM associated to it? It's like we take one state, no hidden variable, like just one completely one state for L.
So no
O.
No latent variable, no.
All equal one state and P. Okay,
So
just
X-
explain X, yeah.
X would be the P of S equal 1 divided by.
Yeah. Okay. Yeah. Exactly. Yeah. Exactly. Okay. I understand. No. So the yeah. Yeah. Exactly. So the. You don't hesitate to ask questions.
For the other direction. Yes, I
Is it X or after X?
No. H of X equals X. What you wrote.
So, yeah. So this is polynomial in, okay,
It's order 1.
oh, it's linear?
Yes.
Oh, it's linear in the likelihood ratio, so the X here is the likelihood ratio.
Yes.
Okay, so it's not all rational functions with non-negative coefficients. It's only ratios of linear.
Yes, but what we want to say is inference on BSM amounts to computation of RFNT. But what we saw here is that for all RFNT, there is a Bayesian predictive model we can build to so that the inference of the BSM amounts to a computation of this particular RFNT.
No, I think that was very clear. If I understand, the last question was just how to interpret X with respect to on the right hand of your equation. You have the variable X, and he was wondering when it corresponds to that side of the equation. Is it states, the value the states can take on, but you showed that it's not the case. It's
Well,
a ratio of probability
The question
of states.
is, we have two
Okay.
Bayesian predictive model,
Yeah.
which computations is the rational functions h1 and h2 of X, which is the variables of the reference we are interested in. So in practice, that means these are the likelihood ratios of like you see here. Here I define the X as the likelihood ratios in X like this.
So like if you start with linear terms for H, HAX is linear, like you're gonna get any sum of you're gonna get any sum of the 1 of X minus C squared, right? Sorry, you're gonna, that's what I'm saying. You're gonna get any rational function within you're gonna get order 2 polynomial up, order 2 polynomial down, and if you start again, order 3 down, and that's how you get everybody.
Yes, yes. And you just have to prove that you have a BSM for trivial RFNC,
Yeah.
like X or 1. So, but this you can do, and
this is really interesting. It means that you take a system, you find a natural way to glue them together.
Yeah.
And this allows you to basically, it's not the multiplication operation, because you're showing how, but this operation is not the, I don't know if it has a name or if it's already like a known operation in rational functions, like the one that you're the ratio of. So when you bind together two BSM, you get in the next slide the operation on the associate rational functions, right? The ratio. So there's no, but it's interesting to see that one you interpret as gluing the system, and the other one just as an operation inside of the set of rational functions. It's not like multiplying them; it's another operation that is like also something it's associative, because if you glue together 2 of them, 3 of them, imagine it's the same and gluing you 1 glue 2, then you add 1 more, same and gluing these 2, and then adding 1 more.
Yeah.
So you're getting a new operation on the rational function that is just comes from the way of gluing probabilistic systems together.
Yeah, and this comes from the work of Pierre and the colleagues, and it's related somehow to data fusion.
Yeah. And it was known before then that you could that the like that the so basically that the so I'm going to ask another question. If you do not normalize by P of S equals 0, but you normalize by the sum, you get a similar function. Because like now you chose a way to, so the coefficients of your distribution, you need to divide so that they sum to 1, right? So you can see them as if they were, you can see your coefficient up to a value, right? So up to the scalar coefficients. That's why you divide you look at the ratios so that you can parameterize the distribution.
Yeah.
Now you chose a specific one, which is to choose one state and divide everybody by this one so that you can get the parameterization. But if you change your parameterization and divide by the sum, for example, would you still get like you get other kinds of operations on the rational functions?
I don't know. It would be different operations, I think, but I don't know what you can do with it.
Because like what you because it's the same operation probabilistically on the probability side. It's just a different way of parameterizing your distribution.
Yeah.
But then there's different operations on the rational functions.
I'm not sure. I will say.
You see, if you have this, then it's very interesting because it means that you have an ambiguity from the way you merge together, the way you parameterize. The way you parameterize gives you different functions, but they should be basically associated to the same model, same PSM. It's not a bijection, your PSM to.
No. You can have multiple BSM mapping to the same.
In the opposite.
Yes. No, the opposite. No, you've got only one. I showed it's this one. It's this one. So you've got only one reference for this.
Because you chose a way from a rush. So you're saying what? Sorry. wait, no, this is saying that you have only from one P a unique RFNC, not the opposite, no? It's not a unique, one RFNC gives you a unique BSN.
A unique,
One BSN gives you a unique RFNC.
one DSM gives you a unique reference.
Yeah, exactly, but I mean like the,
But here you have multiple choice to choose the parameters and to split the operations in different orders, etc. So you will reach different VSM for the single reference. Okay, so now back to biochemical cascade. So as I showed you, what we mean by biochemical cascade is a series of messengers, production, removal, triggered by the macromolecules, and we get a chain like this. And so this is zooming at the production of and removal of a messenger. So you see you've got the input messengers here and the output messenger here. Okay, so this is a basic block of biochemical cascade. And if we look at this, so this is the macromolecule simplified. So we suppose there are two messengers, two ligands which can bind to the macromolecules, and there is a state activated or inactivated. So these are two conformations of a molecule, and so in total we have 8 states, and we suppose that all transitions among those states are possible. So we can write the dynamics for the macromolecules as a Markov dynamics, where we have the probabilities of occupancy of each state, which is at time t, which is the product of the probabilities of the transition matrix times the probabilities at time t minus 1. So then the stationary distribution for such dynamics is can be computed like this. And well, I won't enter the details, but we can rewrite the probabilities like this. And so it looks like it will be rational function for sure, because you've got product, sum, and the ratio here. Okay, so we are not far from rational function. Then you need to prove that the lambda A are 0 or 1, and that's what we did in the paper. And yeah, maybe I won't enter the detail because I don't remember perfectly well. Me too, because it's work I did a few years ago. But basically, what we did is to introduce matrices, what we call almost diagonal matrices, where each element of this sum has determinant which is equal to this. And by doing computation on these matrices, we could prove that lambda is.
so you have an assumption on T now to do this. You
Yes,
assume that T is
sum to 1 on columns.
no, what I mean is the assume that because PI is you're seeing it as being the unique stationary measure, right?
Yes.
So you assume that it's Tn converges to PI, so you're assuming something on T that it's reducible, irreducible.
Yes, but it's true for
Because if it's not, like, imagine you go from, like, there are several things, but imagine that they never. So maybe because here the chemical, the reactions that you're considering, they're always like this. Like probably they have like in the matrix you have no zeros.
you have some
You will
zeros.
have some zeros, but so in this case,
Because you can jump only from this states. So you have rules on the accessibility of states, because to go from here to here, you need to go through this path, or you have several paths possible. But,
okay. But so if your matrix, if your like what could happen is you have let's say paths where you don't go everywhere, right? Like you could say that there's some disjoint union of states and you
Yes,
stay inside.
okay.
In this case, mu pi is not unique,
Yes.
and so you're assuming that you can basically
But it
that
is
you're
true
in.
here. Like every state is accessible from anywhere.
And can you go back on the just on the slides before, explain maybe a bit, maybe you explained it, but I wasn't able to understand it. So like, just before explaining exactly the so just one slide before this one, explaining the chemical.
So you have
the
a
impact.
chemical
Yeah,
reaction
exactly.
where the messenger are produced. So this is this part, this reaction, and removed, or the back reaction. And each of these reaction is catalyzed by the enzyme, for example, the example of an enzyme. And so the enzymes are producing and removing messengers. Okay. And so then the enzymes themselves, or the macromolecules, we have this diagram. Okay, so you see the messengers here, two types of messengers which can bind to the macromolecule.
So it's my fault. Maybe so if I'm too annoying, please tell me that we'll stop. But it's just so here an edge is a chemical reaction, right?
Yes.
So now
Well, it's a transition because sometimes it's just a change in
State of binding and activation.
Yes.
Yes, it's a condition in which for activation, if you wish, you need to have two molecule binding to one.
But so what is acting on the edges normally is a catalyzer.
Yes, the
which-
transition is a.
No. The edges here have no catalysis. The catalysis is on the production of messenger or removal of messenger.
It's a probabilistic model of transition.
Yeah.
I see. Okay.
Because
And typically, these reactions occurs at slower scale than these ones.
Yeah, I understand. So then, depending on the chemicals, so this is conditions to chemical. So you have these transitions, and the transitions are conditioned to outside chemicals that will tell you the probability rate of transition, right?
Yes, because the probability of binding depends on the messenger concentration.
And here in this diagram, this one shown here, there's no messenger concentration at all that appears.
Well, there is on the edges.
Yeah, but it's hidden.
Yeah.
It's like no, just to be sure and understand. Okay, perfect. So it's perfectly clear.
But that's indicates that the configuration of possible for the transition follows this cube number of topology, number of edges and vertices, but there is no diagonal connection between the transitions that are impossible.
And little sun means activated, right?
Yes. Yes, and
But
maybe I
it
should
can
have
also be
said,
activated
I should have said
without
before.
the binding. It's a probabilistic stochastic.
Yeah. But it's important to really get I think it's very interesting.
Yeah, and you're right, but I should have indicated that the transition of the probability of transition from here to here depends on the concentration on the messenger. Because that's why when I look here, I look at the probabilities of transition and I say the occupancies probabilities are RFNC of the probabilities of transition, so of the concentrations of messengers. And so then it's much easier to see that the stationary distribution for the stationary concentration for the messenger is just the ratio of the probability of occupancy of producing macromolecules and removing macromolecules. So it will be RFNC also. So in conclusion, we have the step from BC to RFNC. Okay. And then we can build a reaction, a biochemical cascade for the product. So trust me, this gives the product the concentration of Y is the product of the concentration of red and concentration of blue. Here, with this reaction, we have the sum of the messengers as the stationary distribution for Y. And here we have a ratio. And so then by combining a bit like we did before, for any RFNC, you can decompose it into a step of operations like sum, product, ratio. And so you can build an RFNC for a biochemical cascade for any RFNC.
So do you get, so the opposite, you're saying the opposite, okay, it's equivalent. So any RFNC gives you a ABC.
Yeah. Like
Because I remember in your
here it's a bit involved to show that an EBC amounts to a RFNC. Okay. And here it takes a bit of time to find these reactions, but once you find it, it's easy to build an EBC for any RFNC.
Okay.
And so, as I spoiled before, so we can have a mapping from BSM to BC going through RFNC. And so here is an example for the multiplication. So this is the dynamics for Y, and this is depending on the two concentrations of messengers. So here I call it Z, but it's the output concentration. And when you go at high concentration, it deviates a bit from fluctuations are bigger, but for reasonable concentration, the output is close to.
So the only thing you're cheating about is you're assuming that it's becomes stationary.
Yes.
This is the only point that this is.
Yes. And you're right that it's a problem when you chain a lot of reaction. Actually, you never reach stationary. Well, in
But it makes it more
regime.
interesting. Like even like because like you would have this kind of computation, but then it will never converge. So you get just close to it.
Yes,
So
yes.
it's more interesting to see that you can have this separation on the stationary measures, stationary distributions, but then the dynamics can lead you a bit far away or nothing.
Yeah. So now, I will talk a bit about phototaxis, and we'll come back to this at the end. So yes, this is how you grow microalgae. So this is a growth curve in different medium of microalgae, which I did with Biochemical. And so this is the setup for observing the phototaxis. This is the setup invented by Colliaux with an artist. And so we have a mirror, we have a projector, and here we have the algae in a petri dish, and we have a camera capturing the images. And so we can input any image, and we see how the algae will move. So here is an example. So I put a spot of light here, then I switch to here, and switch back, and you see the algae move from one spot to the other. And at high density, you see that they have some funny patterns. Like it looks like a bit like Turing patterns, or so yeah. So what we study is the distribution of algae as estimated from the level of green. So it's a rough measure, but that's what we take. And we are interested in the maximum density of algae and the slope of the profile to know how sharp it is.
How is this related to the first part?
I'll come to it at the end.
So
Yes. So
you have still 1 hour, so you can take your time really to.
okay.
No, because you have a lot of text, and so you don't have time to read, but it's okay. It's just.
Lot of text? Yes. No, but I explained this. I explained we look at the maximum M here and the slope of the profile. Okay.
Okay.
So
Okay.
how concentrated we are at the maximum and how sharp we are. And these are two macro measures of the phototaxis process, okay, to characterize. So we see that the maximum, so in green is the density at the center. So we see that the growth. So like here is the center, and here is the border of the petri dish. Okay, and you see that first we are uniform in concentration, and then it concentrates on the border, no, on the center, and we see the dynamics for the concentration, and the spatial resolution is so it should be the inverse of the slope. Well, anyway, but we can see there is dynamics for the slope too. And here you see the for the two species, Chlamydomonas and Euglena, as a function of light intensity. And it's nice to see that here, at very high light intensity, actually we don't have a bump anymore because it's too much light, so algae escape. So yeah, and also it's nice to see that it's sensitive to the color of the light. So here you see for different colors, the white, the green, and the blue are okay, but the red there is almost no concentration of algae. And here there are some collective effects, like you see here. It's as if they have some highway to go to the spot. They take some route, and also there are some fun collective effect like vortex like dynamics. And yeah, here also you can see the axis of symmetry have a higher concentration, so it's mysterious to me. And so then we did some experiments under the microscope. So for this, we built a kind of a small swimming pool for the algae. And here you see here it's optical fiber, which comes to close to the swimming pool. And here you see the cells, you see the light here, and the cells gather close to the light. And it's not obvious, but you see, if you look here, there is not so much algae. And so we collect many data like this, and here you see the distribution of distance to the source. So you see that before this is when the light is on. Before the light is on, it's almost uniform, and after the light is on, there is a bump here. And if you look at the average, the distance decreases sharply. And also, what is interesting to look is that the relative orientation to the source of the algae. So you take you take two frames, you take the speed, and you look at the angle between the speed and the vector from the position to the light source. And here you see, just after we turn on the light, the angle is almost immediately zero. Well, at least it concentrates from zero very rapidly. So there is very, very fast reorientation of the algae. So when we look in detail, it's interesting to look in detail at at the trajectories. So you have a helicoidal motion combined with a random tumble dynamics. So you have multiple time scale in the trajectories. And so we can fit a model of random tumbling dynamics. So at short scale, it should behave square for the square of t for the square average displacement, because it's just ballistic motion. And at very large time, we should have diffusion type behavior. And so we can fit the Taylor formula for this. So
what was known before your work on their movements, the run and tumble, because you seem to show analysis of the videos and try to fit from the videos by the analytical model. So was this was not known, right, before the description of their behavior?
Well, there were some quantification on very different algae, the Glena gracilis. There were some quite detailed modelization and quantification on this. On Clavinomonas, not much.
And so it was also use the same method to so I didn't understand your slide before. So what you did exactly, and is it like
this?
so let me see. Tag.
This is
okay.
just to say the random number dynamics. It has two time scales, one at which the square average displacement behaves as a square of t, like ballistic motion, and at longer time scale it behaves like a random walk, and so it's linear.
And the slide after, what were you doing?
So this is to show the formula of the model we fit. So this is the formula for the square average displacement of random tumble motion.
And so
this is the fit, but you see I have several trajectories, but they have very different parameters. So I fit the average, but it gives an estimate of the diffusion coefficient.
Okay.
Yeah. I didn't totally went to the end of this, because what I wanted to do is to compare the microscopic diffusion coefficient and the macroscopic diffusion coefficient. Like when I studied the bumps, you can also estimate the diffusion coefficient from this, and so you can see the two match.
Okay. So if I understand clearly, so you have a microscopic model for the ballistic movement and then the tumble. So ballistic is just go straight, but no, not stochastic basically.
Yeah.
But then you're gonna put up to some points chosen by Poisson. Poisson is something that you fit also. You say I stop, and now I start moving chaotically.
Yeah.
And you do this repeatedly, and then you compute the expectation. It gives you the parameters, which is the parameter of the Poisson distribution and the parameter of the coefficient, the speed of the ballistic move, right? The norm of the how fast you're going to go when you're going to.
Yeah.
Or is it a distribution on how fast you're going to go? It's just the speed.
It's just the speed.
Okay, and then you say, okay.
Yeah. So based on, as I said, I tried to reproduce the bump you saw, the petri dish, and I didn't do it, but we should try to match the experiment to see if the experiment match with the macroscopic experiment. So this is more detailed on the model. So here you see, so these are the swimming motion of the flagella, and you see they can be synchronous when you go straight, and sometimes it tumbles, change orientation rapidly, and at this time the two flagellas are synchronous. So you can model this with core motor oscillator, for example, stochastic core motor oscillator. So this is the simulation of the core motor stochastic oscillator, and yes, this is population simulation, where you see the population going from one spot to the other, a bit like you showed we saw in the petri dish.
So in your models, every alga is within the similar agent.
Yes,
So you have like thousands of them.
yes,
According to this equation.
yes.
I mean, that's for the motor. Well, but that's the transfer equation. There's everything. There's an input as the light, and this is also the vector.
No, input light is a function of is a field in the space.
Yeah. Okay. Yeah. I see.
And did you fit the concentration with the concentration of your images?
No.
I mean, did you compare, not fit, but just compare? Because you can like with your simulation, you get dynamics, you can compute the concentration, let's say over a big but not too big volume, and then compare it to what you see.
Yeah. Well, I did only qualitative comparison, which is to say, like if you take classical random ensemble motion, you don't get this kind of highway, what I call the highway of microalgae, because you would dissolve and reconcentrate if you take a standard random ensemble motion. So here that's why I think there is a need to take into account the relative orientation to the source, because the tumbling rate is affected by your relative orientation to the source. So, yeah. And just a few, so if we want to know, so this is not very biochemical, you know, this is very phenomenological model. And so if you want to go into the biochemical aspect of this, so the I here is a channel rhodopsin. It's the same which is used, for example, in well, it can be expressed in neurons, for example, and you can neurooptics. How do you call it?
For roads, the name of the.
Like you know, you can stimulate a neuron just with light.
Oh yeah, sorry. Yeah, of course. With this more technical abilities.
Yeah.
I have the the whole induced by the
Yeah, but anyway, they use this molecule to be sensitive to light and to generate membrane potential. And so the model for this is 8 state, but you can reduce to 3 state. And here you have some numbers, but maybe it's not necessary. And
So
you can simulate the dynamics of. You are saying?
no, maybe going to try to go into details of the.
Okay, so
Sorry.
if you flash channel rhodopsin, you have roughly 1 million ions, so mostly calcium, but there are others, I think, yeah, potassium and protons, which goes through the channel. You generate with one flash, generate 80 millivolt of depolarization to the membrane attached to it, and and you've got between 10,000 and 100,000 channel rhodopsin per eye spot, and 10 to 100 charges per channel. But so the effect of a flash on channel rhodopsin is to generate a membrane potential close to the eye spot.
It's not the receptor, it's really like it's a channel like yeah, exactly. It's an ion channel that is light sensitive.
Yes.
And so
it's a transducer from light to voltage.
because it's gonna open to this,
Yes.
So when it sees light, then the conformation of the rhodopsin will change. So it will
Exactly.
open, and so now the ions will
The
pass, and
ions
so
will
it creates
flow.
a delta of
Yes, exactly.
And so what are the 4 transitions that we have on the right?
Oh, good question. Good question. I don't remember.
Okay.
But basically, there is open and close, and activated and deactivated. I think it's two.
Okay, I see. Yeah, okay, I see. Okay, because one without light, one with light, and one. So you mean that the
Yes. The probability of transition from closed
but-
to open is going to be higher. It's like.
Yeah, but it's not all. I mean, it's really captures a lot of different stuff in the same.
Yeah.
That's really.
And so here you see the simulation.
Photogenetics.
Photogenetics. Yeah, thank you very much. Yes, and then if you look at the eye spot, there is some interesting phenomena, like if you send some light, like rectified sinusoid like this, and you change the frequency of the rectified sinusoid, you see that at low frequency there is not much. At high frequency, after adaptation, there is not much. But at intermediate frequency, there is the biggest response. So there is a kind of optimal frequency of response of the eye spot in terms of voltage it generates. And it's interesting because 1 Hertz is roughly the frequency of rotation of the eye spot. So the eye spot of, it's an helix. The trajectory is an helix. So the eye spot sees naturally fluctuating light, like oscillating light, because it oscillates along the.
And is it the way, does that play a role in the orientation? You know where the light comes from, the direction of light?
Yeah.
How does that work?
Yes, I guess so, but there
Because
is
it has
not much.
only one single eye spot,
Yes, it has only one.
but somehow it moves and maybe it has some
No, it doesn't move.
polarization of light, or does it?
Yes, there is some effect of polarization of light. Yeah.
That's used as its own referential to transcribe that from maybe in terms of direction or motility.
That's my assumption, but there is not much evidence. I would say because I think because we saw in the simulations I showed before, but it seems that the perception of light direction is important to reproduce the same behavior as we see in the experiment. I think, yes, it has some role in detecting the direction of light, but it's my assumption. But you see, it's a very nice example of adaptation. The optimal time scale for the eye spot is exactly the time scale of action of the motor. Yes, and here a bit more on flagella. So here you see the motion of flagella, and the motion of flagella is related to calcium dynamics. So yeah, it's difficult to say how it works, but well, it's a molecular motor. But how calcium affect molecular motors, I'm not sure exactly. It would be necessary to take this into account in a model if you want to get the model. Yeah. And so back to biochemical cascade. So we can build a model where, so here I call it L and R here, and L1 and L2 here, but it's the same. So suppose you have a way to detect the light on the left and the light on the right. So maybe through some temporal integration or something like that, because at t you detect on left, at t plus delta you detect on right. And you want to infer the probability, you have to go forward based on those two information. So the table is like this. If you have light on both sides, you go forward. Otherwise, you switch. But this is probabilistic.
And how about when it's in the back?
It would be
You assume that it doesn't turn the signal.
yeah, because of polarization effect, we assume that it doesn't see light in the back. Yeah. And so we can write, sorry, the formula is cut here, but the general formula for the odds of the probability ratio of G is this one plus some terms we don't see here. But because we know the table for P of G given 0 and 1 and 0 and 0 and etc., we can reduce the odds of G to this. So it's as you expect, it's a rational function with negative coefficient. And based on this subjective model I showed before, we can build a biochemical cascade which implements it. So this would be a candidate biochemical model for the probability of going forward.
But how do you relate it to the, so you said, trying to make things together. So you have rhodopsin, light, change of membrane potential, and you said chemical reaction, chemical cascade, but you didn't specify how the rhodopsin is related to how the change of the, I probably didn't understand how the change of polarization of the eye is related to there's no relation with the chemical cascade. So is there one? So I'm having difficulties relating what you said before and what you're saying
let's
now.
simplify the message like this: is I have some bits and pieces of biochemical elements, but for example, for the flagella, how the calcium is controlling the flagella, etc., I don't know, and I'm not sure people have an idea on this. So I say let's switch to a Bayesian subjective model. And for this, we can build a biochemical cascade, but which is not related. Maybe it's completely different from the one
Because it's
implemented.
phenomenological.
Yes, yes.
Well, so I'm I don't know algae. So algae are not unicellular.
Sorry, I should have said that.
Okay. So then the potassium and calcium that goes inside and goes out, then it's lost.
No, because they are pumped, and I mean, you're talking about biochemical gradient and how they are maintained.
Yeah, exactly. Yeah.
No, but this is all, biochemistry, then you enter, but
No, but I want to understand because here it's a unicellular, it's not a set of neurons. It's unicellular.
You know,
So how,
the biochemical cascade and change and cycles that are involved, here is focusing only on the basic level of transduction between lights and depolarization of
if you have a, but like,
and on the other hand, you have the flagella, but the whole biochemical network is not worked out. I mean, I don't know if that's what you are looking
no, but
for.
I'm trying to understand something. So the channel opens, right? So you have several ions that goes away. So what was that? Potassium, calcium.
Yes.
Okay, and then you're saying calcium plays a role in the way
Yeah,
that
but it's
the
not the
flagellum.
I guess it's not the same
It's
calcium
not the
because
same.
you've got the membrane potential which propagates, which can go faster to longer distance than the calcium variations. I guess the variations of calcium close to the spot are too far away from the flagella to have an effect.
Yeah, but this is exactly what exactly the point.
What I
Like,
imagine
if you have a
is-
spike that goes away, the calcium, then it's highly inhomogeneous inside of the cell, but the cell is still
Yeah, but now
small.
you have a chain of
Yeah.
biochemical
So
reactions.
is it possible to have like inside of it such a big gradient?
No, but
I don't know.
this is basic biochemistry.
I agree, but I want to just
I mean,
because usually I see it for neurons, but
often
not
so
inside
what we are
of
talking about here is the depolarization that is very local. It's not necessarily that you have a spike that will
But I agree, but if
that will propagate along the membranes, then to serve as a signal for another event remotely to be triggered by that very spike.
no, but you
It can be, but often so it will be that the local milieu around the proteins, G proteins, there's some conformation change, and that induce, this depolarization will act, force on local networks that will triggers, there is a whole chain here. It's not like propagation, electrophysiological propagation of signals to a site, like for instance, from the dendrites to the axon termination to release.
Yeah, but everything is closed in the system.
The whole chemical network is not.
But everything is closed in the system. Like if you take several neurons and you're looking at concentration of, and it's very stuff that I don't know very well, but bits, but not very well. But so probably, but if I say that, please tell me because it's tell me. So, but for neurons, you have several cells, and the concentrations are basically fixed. Things go inside and outside. Here it's open, so it takes out thing, and then it has less ions, so it's going to create like the concentration is not going to be homogeneous. It's not that equilibrium, and then it needs to find a way to get back calcium from outside.
You have organelles in there, and
when the channel opens, it throws away ions.
The conductance are at a different scale. It's not necessarily like the lipid membrane, but you have like the difference. I mean,
because it's one level. It's a one cell level. It's not multi-cell level.
No, but within a cell, you have a universe of biochemical reactions and shielding, resistance, conductance. You have, your organelles are made also of lipids sometimes.
No, this is different. This is not an ion. It's different. It's not an ion. Like it's there
are tons of molecules in there that play on all and their dynamics of they play how the local change in the electrical field. These provoke cascades of active.
My question is just how does it get back potassium and calcium? Because I don't know how it gets it from outside.
My guess is that the calcium variations will be very close to the membrane, and so.
But how does it get it back to keep a certain concentration, fixed amount of mole of micromole of I don't know the scale of calcium?
Well, it's an equilibrium. Channels open and close.
So you get it from outside.
Yeah, they are
like in the water.
Consume energy, yes.
But the milieu where it is.
Yes.
So okay.
It's a bit like it's like no.
Yeah, but but if it's for me, I didn't know calcium was something so very common to find in the water or things like this. No idea. So it's
I guess people
calcium, potassium, and everything is very classical to find in the water.
They are grown milieu.
Yeah.
Or minimal or
Okay.
whatever.
Yeah.
Usable, and in this you add some minerals.
Okay.
So
So you have this, but you have one part at the part, but you don't have a full idea of the chemical cascade. So you use a Bayesian like a phenomenological model. You construct a Bayesian molecular cascade. But now my question is, so this molecular cascade is purely abstract. How do you relate it to one part of the molecular cascade you already have, or some parts of that some variables of your cascade should relate to things that that are useful in the real cascade. So how do you have a way to constrain your model to things already?
Not much, but one difficulty I have to do this is because, as I said before, I assume that L1 and L2 are two measures at different time. Because it's along the helix. So it breaks a bit the framework we had in the first part. And so it's difficult to match the two. But
okay.
In fact, the idea I think is that there is a generic library which is the building block of your overall model are to be basically basic transduction mechanism between messenger molecules and the molecules that will then create the response. Those are messengers. And then there are some constraints about probabilities of transition between basic systems. And then the idea is that change of biochemical reactions after all somewhat are always similar to that. So change them.
Yeah, but I think it's
to build the pathway, but then you don't have necessarily the data and the knowledge to be precisely and conformly to the biophysics of what's going on in this area. So you use this phenomenological model, but then the question is, it could work both ways. There is some sort of duality between your Bayesian expression and those kind of means through this rational function, these kind of basic models of biochemistry, you feel that, you know, if you develop that, there be some criteria of heuristics that could guide actually by making prediction about data, differential prediction with some sort of Bayesian framework. For instance, you test one version of your model chemical cascade versus another one, you get the predictive power compared to Bayesian prediction. So would that be used, you feel, honestly?
Yeah, actually, what
as a heuristic.
with Grégoire, we would like to take several different subjective models and see how it affects the dynamics of a population. If there is some differences on the trajectories, maybe we could identify some features of the trajectories which are indicating one or the other of two models.
What you could try to do, because this reminds me of old work I did in the whole science, when you have so much uncertainty about the detailed realities of the biochemical networks in this complex from it was neural networks, it's anatomy, pharmacology, etc. And we're obliged to make a lot of simplification, and you know, for instance, you'll end up with 5 modules of chemical reaction when there are 10,000 million. Could be actually involved, variety of them. So then for it to be interesting, because obviously it's necessarily degenerate, it's important or useful to try to find classes of models that are well distinguished in terms of, for instance, their architecture of pathways, the way they connect to each other, while being compatible with generating the phenomenon of intelligence. So the transition model. And ideally, what you would like to do, and by looking at the literature on the specific ID or even more general biochemistry, maybe there are clear hypotheses about, you know, for instance, well, there are those main pathways that are involved, but there is this other guy that says that actually instead of having 2 parallel pathways that process different information, you have, you know, some sequential. If you can get that level of abstraction, as you can sometime in neuroscience, because about, you know, occipitofrontal interaction, and there were hypotheses that maybe there exists direct shortcut versus no, there is this sequential stuff, even though there is accuracy. You have very broadly different architecture, like you could say for simplifying parallel versus serial. And then you could test its predictive power with generative model for measuring, for example, magnetoencephalography. A model called dynamic causal modeling. So with this principle, if there is enough from the literature to at least constrain a bit different class of architecture, then you could actually even go from the class of architecture back to your Bayesian subjective model and define the subjective model. And then it will be very interesting to confront that to empirical data, because you have more chance to have discrimination power, and it will be relevant in terms of conclusion. And we can conclude, well, actually, we don't know exact detail of these things. That's all this involved in the abstract map. But at least all the models that have the best predictive power, they follow a certain type of architecture.
Yeah, as I showed you, there are many paths evolutionary which led to phototaxis. So we can
that
imagine
could also be a process. And at that level, with a comparative method between algae, instead of within an algae testing different. Yeah, that might be more tractable. Interesting.
Okay, maybe a few words of conclusion. So yeah, so we have data for estimating parameters of the model of phenomenological models of microtaxis. We can have a Bayesian subjective model implemented in biochemical cascade. Also, I was interested at the time at the link with photosynthesis, because the microalgae they like light because of photosynthesis. So it's interesting to see how the two interplay. And actually, now in my work in Sony, we look at the photosynthesis of microalgae, but not really at the phototaxis. So I still have to link the two. And also at the time I was in a robotics laboratory, so I thought it was a nice minimal model of agent, which could be inspiring for micro robotics. And so you see, you have here some beads that people can control with light, and they can move cells precisely with light. Here it's a micro robot where they can make U-turn just by changing the magnetic field. Actually, it's a passive magnet, huh? But they can make them U-turn just by switching the magnetic field. And here also, I was interested in smart dust. So it's very small microcircuits. And to program this kind of microcircuits, you use light again to program, right? So you can do a lot of things at the micro scale with light. And, well, thank you very much again for having me, and thank you for your attention.
Thank you very much.
You did not write this paper together. We wrote a paper about mRNA transductions to ribosome.
Yeah, no, it's
And
not
the
together.
Bayesian-
No, I cited his paper,
Yeah, you cited him, but that was with another colleague of yours.
Yes.
Right?
which was a colleague of Daniel, your team seat.
Yes.
So, and so that's how I knew, started to know his work, and it's
Nice.
by reviewing the literature. Okay, is there any question in the audience?
Is there an audience? Thank you. After one, forget that.
Yes. So okay, so when you got your computator chemical cascade at the end, were you looking to try to check some like were you trying to look at the cell and see if this actually is a predictor for it, or
No, it didn't that time. I would have liked to implement, to generate trajectories using this model, but I didn't have time.
No other questions? So let's take again, David and Ken. And let's maybe go drink something. Okay, so thank you very much for the audience for attending this new session, and hopefully you like it.
Qu'est-ce qu'il utilisait comme micro?
And see you next time.